let's look at two examples of finding the area of a regular polygon. First is going to be a hexagon. Its radius is 20. Here, radius of a regular polygon means distance from center to vertices. Notice that's going to be like QL as indicated as 20 or QK or QP, etc. There's a different measurement, which we're going to very much need, which is if you drop an altitude from the center to any one of the sides by the symmetry of the thing, that's also going to be a perpendicular bisector. And that is going to be the perpendicular distance from the center to each side. That's called the apothegm. Okay. And so that, in this case, is going to be QR. So we're going to want that. The reason we're going to want that is we're going to think of the hexagon as a bunch of copies of triangles. You can think of it as a bunch of copies of KQL. That's certainly very useful. The hexagon is some number of copies, think about it for a second, of KQL. It is 6 copies of triangle, didn't quite work, KQL. And another nice thing about the hexagon is that that triangle is very, very special. If you think about what those angles have to be, we see that that is equilateral. That's very special to a hexagon. Only a hexagon has the triangle made by a center and the center and 2 consecutive vertices being equilateral. But it's certainly nice when you have it. Okay. But we actually turn out to more often say, actually, I really like right triangles a bit better because that's where trig applies. And so I actually don't want to say KQL. I want to say RQL. And then it is 12 copies of RQL. So that's actually how we're going to think about it more often. Okay. So if I can just get the area of RQL, I'm going to multiply by 12 and I'll be done. Okay. So let's go back one more thing about the equilateral. That means that KL here is going to be 20. Okay, and I can also then say, oh, hey, but then RL is just half of that. And that's going to be 10. Either way, for a hexagon, you can kind of do it either way. But for more general polygons, we're going to look at the right triangle. So we're going to look at the RL. That's the half of a side length, right? So half side length is really useful. Okay, so we've got that half side length, which is the base of RQL. Now we just need to get the height, and that is exactly that, apothegm. So that is QR. That equals the height of RQL. And that's where we bring in the trig, but it's really special triangle trig here. And we know that QR, let me display this, QR over 20 it's the long over the hypotenuse, and that is root 3 over 2. Good to have that memorized. So QR is going to be 10 root 3 when I bring it over, and the 2's cancel. And now I'm almost ready. So area of RQL, I just bring that down, is 1/2 times the base, which is the 10, times the height, which is 10 root 3. And that is 50 root 3. Okay. And now the total area of the hexagon is 12 times that, which is going to be 600 root 3. Now there's a little shortcut here that there's a master formula that says the area of a regular polygon is just always 1/2 of the apothegm times the perimeter. Let me write that out. with the words apothem times the perimeter. And that just makes it ever so slightly quicker once we got that information. Let's just see how that works. If we use that sort of memorized shortcut, then it's 1/2 times that apothem. Remember the apothem was 10 root 3. That was still a crucial calculation. You can't avoid that in this kind of case. And then times the perimeter. Well, what was the perimeter? That was the whole side length was 20, and there's 6 sides. Okay. Is that really a lot easier? Well, here's a 5 root 3, and then times 120. It's still 600 root 3. It's not really that much of a shortcut, honestly. And the way you prove this is to do exactly the analysis we did of taking it down into right triangles. So let's look at another case in 1 sec. So this is a regular octagon. I'm going to have still the radius is going to be given. There's lots of variations where you're not always going to be given the radius necessarily, but the radius is 8. And so that's IB as indicated in the diagram. And I want to follow the same steps, but I don't have a special triangle anymore. So the key is, what is the angle IJ or JIB? What is angle JIB? Because if I know that, then I've still got a right triangle here. I can still do trig, but I'm going to have to use calculator trig and not this kind of fairly pretty, don't have to go to the calculator special triangle stuff. Well, let's think about it. JIB, that's half of the angle AIB. So let's first think about angle AIB. Well, the key is that there's 8 of these pizza slices. I can make this pizza slice on AB, BC, CD, DE, EF, FG, GH, HA. There's 8 of these guys, and they have to add up to 360. All the rotation, all the angles around a single point always adds up to 360. And so AIB is going to be 360 degrees over 8. That's the number of sides. And so angle JIB is going to be 360 degrees. Oops. Over 16. People often miss that too because we're looking at that half slice. Like you cut yourself a big slice of this octagonal pizza, then you're like, you know, I'm on a diet today. I'm going to just take this half piece that makes a right triangle because that's where the trig's going to come in. Okay, now that's 22.5 degrees as it happens. Okay. And so that allows us to find the crucial things. We want to find JB and IJ. Okay. So what are we going to get? We're going to get JB over 8. That is opposite over hypotenuse. That's going to be sine of 22.5 degrees. Let's let the computer calculate that. Okay. So that's 0.38. Let's do 3 decimal places, let's say. And so JB is going to be 8 times 0.383. Let's let it calculate that. And so that's going to be 3.064. So we are sort of going on a calculator direction here. Okay. So that's JB. That's half of the side length. Okay. And while we're working that right triangle, let's get the apothem. That's IJ. All right, so this was the goal here was half a side length, and that's going to tell us eventually the perimeter, or we can just use it directly. Either way, it's kind of like I did 2 ways with the hexagon. IJ over 8 is going to be cosine of 22.5 degrees, and that is equal to 0.92388. IJ is equal to 8 times 0.92388. I guess I'm keeping a few more decimal places here, that's fine. And so that's going to be 7.391. I'll keep 3 there. Okay. So if we use the CAN formula, area is 1/2 apothem times perimeter. We got the apothem. It's just it's sitting in front of us. That's IJ. We still have to do a little bit of work to get the perimeter. What did we get? JB was 1/2 of one side of an octagon. And so to promote JB to be the entire perimeter, we're going to multiply by 16. So there's not an 8, but a 16. And that can be a little tricky. And then that's times the 3.064. Okay. So there's your apothem. We got it from a cosine calculation. There's your half side length. Got it from a sine calculation. There's your how many half side lengths are in an octagon, and then we put it into that master formula. Again, even if you forget this master formula, just find the area of this one triangle. That's basically everything here but the 16. Like if I hide the 16, that's exactly 1/2 base times height for the right triangle IJB. And then it's using the fact that there's 16 of those, 16 half slices of pizza in an octagonal pizza. And what do we get for a final number? It's going to be pretty exciting. 181.7. Okay. And that's, I think, all I want to show this time.